Okay, so welcome everyone back to the World Logic Day. Happy World Logic Day to everyone again, for both here in the room, in the Robert Record room, and also online, the participants who still stay with us. Welcome. So we are in the Robert Record room, and just to say, because now it's getting a bit more historical, Robert Record was a Welsh mathematician and logician, philosopher in the 16th century, and he has invented the equality sign. So now it's a pleasure to introduce our next speaker, John Tucker, who studied He started in Bristol and in Warwick. Then he worked in Oslo, in Amsterdam, and in Leeds. And before joining, about 38 years ago, Swansea University. So we are very happy to have him here, obviously. John was head of department for about 15 years, head of school for 5 years, and pro-vice chancellor for another 5 years. So he is looking back to a rich of experience, we can truly say. So John will now give a talk about the historical aspects of logic. So scenes from the history of computability theory. So John, welcome. Thank you for giving this talk.
Thank you very much, Monica. Right, so I've chosen this title because computability theory is very big, and it's had a profound influence on all aspects of logic in different ways, and also has done rather great things outside logic. So naturally, in a talk, however long, even if it was much longer than today's, the best you can hope for are some scenes that you can reflect on. I hope to get through all the scenes, but let's see. So first of all, it is a historical thing. The clicker's not clicking. I can
try it.
Right, well, thank you. Oh, jolly good, right. So if you want to talk about computability theory in its broadest sense, there are many perspectives, and in particular, these four I feel that I will be able to touch upon in this talk, albeit possibly in a shallow way. So how does computability theory relate with philosophy and logic, and in particular mathematics or some parts of mathematics, and obviously with computing and AI? What's missing here is, does computability theory have connections with the physical sciences? The answer, of course, is yes, but I won't be covering that aspect. So what I thought I'd select on is I'd look at the early computability theory on natural numbers and on strings. I'd worry about the Church-Turing thesis, and then I would possibly refer to these kind of generalizations and applications of computability theory, of which the pluses mean I reckon I can get through them in this talk, and the minuses mean, yeah, we're into the hundreds of slides when you get to that. So I disciplined myself a bit more here. But in terms of giving you an impression of how to think about computability theory, it's good to keep the whole big picture in mind, even if we only manage to see a little bit of it.
In the room.
Everything all right? All well? Good. Right. Now, so let's start. What did computability theory ever do for philosophy? Philosophy, of course, as we all know, has got something of an ownership issue for logic, which we will come to. So the connection, of course, is in that part of philosophy that in the Western tradition we call epistemology, the theory of what we know, how we know it, how we justify what we know about what we know, and so on. And so let's look at that theme. And unsurprisingly, we should possibly start with Frege. Now, Frege as you can see, is very much a 19th century mathematician. He felt that there were some very deep weaknesses in arithmetic, in the way we talk about arithmetic. And when you see things like that, you really got to think about what did mathematics look like, let's say, halfway through the 19th century? What was going on here? You know, I mean, we all possibly are aware that within the mathematical corpus, all kinds of theorems were claimed, which later on, as the subject developed, turned into specialized versions of more general theory. So the great names from analysis, for example, and so on, that were dominating it. And he introduced, in order to tackle what is arithmetic in a more rigorous way, he did some very spectacular things. So the first thing is that he introduced a special logical symbolism to get a more iron grip on statements. What are these statements that are in, let's say, arithmetic? And in fact, that's what he was interested in. And he wanted to say that in addition to getting a better expression, he wanted proofs, which were, of course, around. That's what mathematicians have always been interested in. But he wanted these proofs not to have gaps. They wanted to be step by step, accountable, right? Accountable proofs. And this logical symbolism was going to do the job. And from that comes the first stirrings of the idea that arithmetic can be derived from these symbolisms, which he saw as part of logic. Now, logic was 2,000 years old. And it's not the case that he was the first person to worry about logic, because we've seen Boole operating mid-19th century. But Boole was essentially an algebraist, and he was looking at these logical issues with a very mathematical eye rather than a philosophical. So what we see here then is a chain of books. The first one introduces the symbolism in the 1870s. Then comes larger volumes, and finally the magisterial 3-volume work, The Basic Laws of Arithmetic. But in 1903, there's a letter from Bertrand Russell about contradictions that he has found in the logical setup of Frege's logical system. So we'll come back to that. In fact, it's an old tune, but in the effect of it is while the volume Basic Laws of Arithmetic are actually being printed. So
how were proofs written before Frege? Not using symbols or like straight?
Oh, the way an applied mathematician in engineering would write it.
Okay.
If I can. Yeah, that looks so wrong. In other words, lots of good ideas of how things work, but not entirely complete. Definitions were a problem. I mean, if you take, for example, uniform convergence, just look at uniform convergence, uniform continuity. These are called uniform, this, that, and the other, because originally people thought they were continuity, and there were extra hidden assumptions. But people had already found out that there were gaps in Euclid. So the more forensic, logically minded mathematicians were looking at the assumptions of Euclid and finding, oh, hang on, you can't prove this particular fact in Euclid on the basis alone of what was in the book. And that wasn't easy to do, because Euclid is an incredible achievement. Anyway, this is the logical formalism. Okay, there it is. And fortunately, we have this table which tells you what it all is. And just looking at it, you see that what we have here is first order logic. First order logic in a two-dimensional display. Now, you can imagine how in the 1870s, when mathematics and physics is often confused, right? Something like this would come upon an unsuspecting world and be incomprehensible. And it's not surprising, therefore, that Frege's work was rather neglected because he has an obscure problem, fussing about what is arithmetic. Huh? Right? A really arcane question for the mathematical community, who, by the way, hardly knew what a real number was. Remember, we often refer to Cantor's construction for the real numbers, and Dedekind will lap after this. And secondly, Cantor, who was starting to become well known in certain circles, possibly not always for good reasons, with his controversial work, wrote a devastating review of Frege, being really very aggressive about what kind of silly prop thing is this. So the forensic analysis, which is clearly logic and a big step forward in logic, okay, because obviously from Aristotle onwards and the medievalists, logic is essentially propositional and not reinforced by Boole to some extent. Frege was hardly known. And what's interesting is, although we may well know now Frege, he really was hardly known until after the war, when logic starts to take off. So we'll see that logic taking off a little bit here, and that's when Frege gets to be much better known. Of course, Frege was acknowledged by Russell. Okay, so Russell and Whitehead were working and beavering away, and they went, and here's Russell, a lovely photograph of Russell from 1936, a very important year, of course, for computability theory, you probably are aware. Russell had already taken a great interest in mathematical issues and had started to write already before the 20th century. And he was also interested in all kinds of other things. He wrote about 60 odd books and about 2,500 papers. So there's plenty of material in the Russell archive, not least his correspondence. And if you want to see it, it's at McMaster University in Hamilton, a wonderful the building devoted to Russell's archive. I must say, it's quite a thing. Anyway, the period we're dealing with is around here, because he had started to work with his mathematics tutor as a young man, Whitehead, and started to work on the Principia. Now, the Principia is a 3-volume work which came out over a period of years, as you can see. And the aim was to fulfill this idea that you can derive arithmetic from primitive logical assumptions with a very sharp logical notation. And this is a very interesting thing that we like to show to give an impression of it. This is a thing that appears that is essentially the 1 + 1 is 2, and that is deep in the book. So we have this activity. Now, what happens with all this is that Whitehead and Russell go to Paris in 1903. So this is coming much later. And there they meet Peano. And Peano tells them about Frege's work. And that's what leads to that 1902-1903 disaster for Frege. Because when that letter arrives and the inconsistency is clear, we run into all kinds of issues about how to repair it. And it isn't repaired. But Russell wants to repair it. And the way he repairs the paradox is this book, in which a notion of type is developed, Russell types, and a type theory is developed, and you can look at the book and have a feel of it. Of course, not a book that you necessarily read easily, but the first 54 paragraphs are quite interesting, and we get to as far as that. Well, are we moving here? Oh, yeah. So there is a very important background to all this. And you've got to remember that logic, mathematical logic, first order logic, things of this ilk, become known because of Russell. Okay, so although we know now that there's this incredible work by Frege at Jena, the answer is there's also this incredible work of Russell, and it is through Russell this thing starts to take off within philosophical circles. And that starts to attract philosophically minded mathematical people. And because, of course, it is very clearly a formal system, one in which mathematicians can feel at home. So we're going to have a gallery now of people that we can talk about, because the beginnings of computability theory we'll see in a moment. But let's look at the people we might meet. Of course, there are thousands of people that we ought to meet in a talk about the history of computability theory. But the reality is we're going to be looking at a small number. So here is Dedekind on the left, and as we saw in Arnold's talk, piano on the right. Then comes Skolem in Oslo and Hilbert. Then, of course, we have Gödel. And, of course, his friend, we spend time on that, but it's always important to remember what circles are surrounding our friends. And there's Rosa Peter, and, of course, Steve Kleene. So these are the people that are now going to be, in various ways, building the start of computability theory. And of course, and I mean image post, I'm not forgetting your post, which we will see a lot of. So first of all, it's not called computability theory. It is all about induction and recursion. So what boils up from this work is an interest in recursion. And already Dedekind, who had worked in the 1870s, published in 1888 his theory of natural numbers, in which he used the axioms that we would recognize as Peano's axioms, which are later, by the way, and this technique for defining things, primitive recursion. So we can see that in addition, in Dedekind, we have a notion of structure, and we have a notion of isomorphism between structures, and we have the famous second order categorization theorem that second order induction all models are isomorphic. So that is in Dedekind's book, notes, which becomes a book from that period. So this is the important thing that suddenly starts to get picked up. Because Thoralf Skolem was motivated by the construction of arithmetic in Russell and Whitehead's Principia. So he was studying Principia. Now, Skolem was a professional mathematician. He had theorems about all sorts of things in his career, but he was taken by these incredible logic developments, which were beginning to filter out, because Principia was not just an amazing looking thing, it also had on it huge claims about the foundations of mathematics, which were known to have difficulties. And in particular, he got very interested in induction and, of course, recursion. So he started to study this as a mathematical topic, which it is. We tend to forget that because it's all sort of now taken for granted and so on. Of course, students always get caught. But in particular, he looked at a wonderful thing called causal valleys recursion, which is very important. Definition by cases and double recursions. And he managed to show that you always get the same class of functions. So suddenly, because he's working on the natural numbers, by the way, you get quite a lot of results. And you can look up his material, but also there's a wonderful note on Skolem by Fenster. So Skolem was very important. And of course, Skolem is also mentioned because other theorems in logic, not least, he was the first person to see non-standard models of the axioms, of course, and they're very Lowenheim-Skolem theorem and so on. But this was a topic now, recursions. Recursions is a topic, okay? And the question about to what extent this is computability is unclear to me. It's very much more a matter of coming out of logic. It is logic.
That's one question. And so when did the school study these recurring notions? Was this, so you mentioned this paper in 1923. Is it around that time or?
I think it's earlier than that as well. I think there is a, if you try looking up Fenstad's thing, you'll get a better thing, because Fenstad works on computability theory and pays proper attention to some of that. But it is a very important step. Scholem is very important in the emergence. And of course, it's now in the hands of a professional mathematician. Okay, and a good one. We also know, of course, about Hilbert's interest. He'd been looking at axiommatizations in geometry, which produced the axiomatization of real numbers of the Archimedean ordered field notion. Is buried in that work. And he was very interested in formal systems. And it's he who was more concerned with simultaneous recursion, which pops up again in the 20s. So this thing is taking off. Remember, Principia, you see, is now only a few years old when this stuff is starting to emerge. And again, the whole question of this recursion, which is now, we know a lot about recursion, or we think we do. Question is just how powerful is it? And of course, the answer to that is the Ackermann function. So suddenly you get this power question. Oh, this recursion is doing well. You can edit it, you can add features to it, you can do all these things with it. So just how powerful is it? Seems a long way from primitive recursion. And of course, it turns out to be because of Ackermann. Now, Skolem's methods are promoted in Hilbert and Bernays, which is the great tome in logic from the 1930s, the early 1930s, where a huge amount of quiet knowledge is registered. And so Skolem is very visible in that, which of course now is overlapping with the life of Gödel, who comes out of nowhere, so to say, and delivers a whole pile of things that we celebrate, not least Gödel numberings, the importance of primitive recursion, and so on. And also Rosa Peter, who I mentioned earlier, was very much now full on this schematology of recursion things. And in her book on recursive functions is about, guess what? Recursion. Wall-to-wall recursion. So if you're a modern person and you think you're going to be reading about computability theory, which of course would be my situation when I came to the subject, this incredible session with arcane examples of recursion was quite interesting, but on the other hand, it seemed to be different. And the reason is it's coming out of this business of recursion induction. It's similar and related, and it is all coming out essentially Principia. And remember what Gödel's paper is called. It's about incompleteness in Principia. Principia is mentioned in the title of Gödel's paper. Just as in Turing's paper, the Entscheidungs problem, which is again a Hilbert Ackermann issue, is mentioned in Turing's paper. So by 36, things are starting to take off because Church, which we haven't yet met for a good reason, and so on, has Kleene. Now, Kleene turns out to be one of the great figures in this development of logic. And in particular, he has this incredible normal form theorem, which is very important indeed as a theorem, because from it, all kinds of goodies come. Of course, when we meet the normal form theorem, we can have all kinds of intuitions overlaid on it so that it starts to become more comfortable. But coming out of the blue, of course, and with Steve Kleene's particular technical style of meticulous detail and no holds barred rigor, it's not so easy, to say nothing of his attraction to Gothic fonts. So, and of course we have now the equivalence, because what we see here is that lambda definability, which we will meet shortly, and recursiveness are known to be equivalent by 1936. So, I've jumped ahead here for 43 because I think when I was designing the slides, I wanted to talk a lot about cleaning, but I haven't got time. So cleaning is everywhere in this early phase. Okay. As I'm sure those of you who do high types are very familiar with that. You've got another version of the T predicate, which is very important, where primitive recursion shows there's basically that least said later on becomes something important in programming. So when we get to programming, I hope to remember to mention to you how that shows up in structured programming. But most importantly, we start to see the arithmetical hierarchy. The arithmetical hierarchy is truly beautiful. It is a magnificent achievement to have the arithmetical hierarchy, because what it's basically able to do is to use the logical definability notions of different kinds, and Arnold was talking extensively about that, and to recognize sets and to classify sets, so that someone would come along with a problem like, what is the complexity of deciding whether a program holds on all inputs, and so on and so forth. And you can rack yourself up in there, in the hierarchy, and easy to find things at level 3. But of course, what it really means is that computability, at least on the natural numbers, is the same as definability in a formal language. Now, in computing, stepping perhaps into an entirely different frame of mind, this basically says that a specification language, notoriously first of all logic, is capable of specifying a computational, operationally computational objects. So questions about equivalences of this kind can be, on certain occasions, easily re-explained as the fact that we know already in the 1940s that the power of these logical formulae, which of course will come from Frege, okay, actually define key computable things like the algorithmically listable sets, the signal one set, these are recursively enumerable. All of this is done with recursive, and this is the great paper that Cleany did for that. And he mentioned that what we would call the church Turing thesis, by the way, in there. It's just called thesis 1 there, but we're coming to the church Turing, because at the end of the day, we're a little bit in the umbrella of philosophy. Here are some references if you wanted to pursue this. Apart from being able to talk to me about it, there are things you can read. And not least, one of the most importantly things is in the IEEE Annals of the History of Computing, made famous by Troy being the editor. And there was a paper by Cleany years ago. So, and of course, there's Martin Davis's wonderful collection of papers on computability. Martin Davis, well known to many of us, of course, was a pupil of Post, and make sure that Post get proper treatment in the volume. So now we get to the Church Turing thesis. So here's Church, and here's young Turing. And remember, the Turing paper, he was 24 years old when he wrote that famous paper on the Entscheidungs problem and the Turing machine and universality and undecidability on the halting problem. But in particular, there's a question mark about this very important paper, which is deservedly first among the equals, because there will be many models of computation. We've seen recursion being really a classic one coming straight out of logic, out of the world of Hilbert and so on. But this machine-oriented notion that we're going to see in a minute is very dominant. Of course, for Church, he had taken a rather formalistic view. He thought that functions were everything, And what we need is a calculus for writing down and manipulating functions, and that is now known as the lambda calculus, of which there are many forms, many shapes, and has had a profound effect in the development of computing, not least in AI, through the way in which it was raided for ideas for Lisp. It's very important to remember that fact about Lisp, and in particular in proofs. So here's one of the fruits of that, 1936. Already, Church could see there were problems that could be non-effective in the sense that the lambda calculus is not going to be able to solve these problems. And in Kleeni's Introduction to Mathematics, which came out in 1952, the great book on logic, which many of us used in various ways, Kleeni's great book calls this Church's thesis, Church-Turing thesis, as we would call it now, and so on. But of course, there's more to this, because if you look at Turing's paper, what you have there are all sorts of things, of course, not least the model, but every real number that is effectively calculable is computable by a Turing machine is basically what you can extract as a form of Turing's thesis. But we would then reprocess that later on, because later on he rephrases it away from the 1936 paper in a more general way. Every effectively calculable function is computable by a Turing machine, because of course he is now aware of Church. And Church talks about effective calculability. So, but for Turing, and this is very important in my opinion, to appreciate this and to see how these historical things are alive and well in our current thinking, is that effectively calculable for Turing is calculable by a person. A person using symbols, systematically working their way through. That is what it means. And there's, of course, the Turing machine. There are many Lego models and all sorts of things. And that's a particularly attractive one, I think. So in 1936, which is often seen as the year of Turing's paper, which it is, in fact, Turing's paper. Poor old Turing's paper appeared in December 36 and also in January 37, which is annoying, which is why often the citations are a bit annoying. We have that, if you want to come and see it, I think I've shown it to some people. We have that in the History of Computing collection, we need to expect. But by that time, you've got these kind of models. You've got the lambda calculus, which represents, again, a formalistic thing. Now, Church was very fond of Frege, was aware of Frege. He's one of these people that was actually more aware of Frege. Then there's the general recursive functions, which we've seen a lot about as being crucial for the mathematical inclined. Notions of reckonable in a formal system start to emerge, using equations, for example, and so on and so forth. And then Post had his own view, and Turing had his own view. And these two had a human being as part of the intuition, explicitly. And if you look at the way the theory starts to develop, you start to see something that I think is worth drawing your attention to briefly, that there are pros and cons. So what we all know is that these things are all equivalent. And of course, that's usually seen as a great thing, because we've now isolated a fundamental notion, which we can ascribe to human beings if we want, and some people do, and everyone will have had their entirely own unique introduction to these notions. But of course, the fact that they provide lots of intuitions, that's true, that they characterize notions very nicely. And of course, because of this convergence of these different notions, it's clearly relevant to the question, what do we know? Because much of what we know is coded as what can we calculate? Okay? What can we decide in finitely many steps? But there are cons, because now we get into the mood of expecting notions to converge. That there are distinctions we might like to make that are not made, and there could be some misleading philosophical interpretations, which is easy to do. I mean, computability depends on representations, and they're not always equivalent. And in particular, we know from various modern theorems that if you look at numberings, incredible things happen. I mean, one of the most important sources of our modern knowledge are the Siberian school in Novosibirsk, where chains of generations of logicians have produced extraordinary results in this area. And of course, Goncharov's theorem is a particularly important one. And notions of computable real numbers, they're also not equivalent. Moskovsky spotted this early in 55, but there are some easy examples, of course, as well. So we know that instinctively their representations can play a role. And so in the struggle to sustain the fact that everything is stable and it converges, we sometimes have to zone out some of these annoying points. Now, this is, of course, not so obvious in some of you who are working, and I'm very happy to see many representations and so on. But I think that's one of the things that you get. And so you lose you lose certain distinctions as you crowd in on this classical computability that we can now ascribe as the discovery of 36. The fact is, I mean, computing doesn't it really depend on where you start with? What operations have you got to start with? Now, if you're doing natural number computation recursion theory, you are making a wholly in stone that the natural numbers, naught successor, great. And that is the theory. But when you think about computation, if I give you some operations, you can do finite computations with them. And it's not obvious that you need to start with 0 and successor. And of course, Turing was aware of this because of the notion of an oracle, which later appears in his work just before the war. Anyway, so surely also there are certain things. You mean, obviously coding in the natural numbers is beautiful because bloody polynomial coding, so that you can have n tuples coded as a number. But you could say, well, hang on, I'm interested in computation. Surely the more memory I've got, the more I should be able to compute. Okay. And of course, you could say in the world of Turing machines, are k tapes better? Oh, sorry, worse than k plus 1 tape? And what about heads? And so on. So there are all these questions that are lying there, awaiting a whole new generation. And of course, that generation has come and tackled a lot of these questions. But these are just things, warnings, if you like, in hindsight, warnings from things. Because the excitement of the 36 situation, as I can call it, it is very profound. But now the other question is, can we work with the intuitions? You know, can you go back to these intuitions and draw things out? For example, what does computable by physical mean? Mean. What does that mean? And so on. So, and how many more intuitions can you cook up? So this leads to the question, well, what is the Church-Turing thesis? Is it a definition? Is it a working hypothesis? Is it some sort of criterion? Is it a theorem? Is it a conjecture or a thesis? And it's commonly assumed as a working hypothesis in continual need of validation, in the sense that you have to buy into it and it might be wrong. So historically, there's something to discuss, but it certainly wasn't seen in these terms in 1936. So the question about the Church-Turing thesis is a natural one that needs some sort of arguments. Now, Turing's analysis, if you pluck it out from the paper, is essentially listed here. finitely many symbols, a workspace ruled into squares like in an arithmetic book. There are finitely many states of mind, and the actions are determined from one state and the contents of a square and so on. And this kind of analysis directly turned itself into the simplified model of the Turing machine and so on. So this is a kind of description. And you could then argue that there's a theorem which is kind of reasonable. If a function can be computed by a human being, following a systematic procedure to manipulate symbols of the kind I've just described, if a person can do that, then what that person can compute under the assumption they can always have more paper, then it can be computed by a Turing machine. Of course, the argument is, do human beings belong in theorems? And of course, the answer is yes, if you want them to, why not? And now we are flirting with AI, aren't we? Right? I think given this talk 10 years ago, no one would think about it. Yeah, maybe. But the AI is all over it, believe it or not. So this argument was beautifully advocated by Bob Sowar. And fair play, it was very nice to be able to listen and talk at length with Bob in a way that did not involve filtering human degrees. Fair play. And I think he hit that, he was able to formulate this very well, in my opinion. And I think it's just simply a good way to look at Turing's contribution from this angle. Of course, the mathematics is still there. The Turing machines are still undecidable. There's still a universal Turing machine and so on. And now the mathematical theory takes off. It takes off really with one paper, in my opinion, or one dominant paper, and that is Emil Toth's paper in the Bulletin of the American Math Society in 1944. And in there, if you read it, you get many one reductions and the degrees that you get from it. The beautiful notion of an immune set and simple sets. You get Post's theorem, which is a triviality to many people today, but it really set the scene that you could make something of this stuff. And of course, the problem about sets below the halting problem, whether or not they are mutually dependent in terms of degrees. So, and these are lovely theorems. I mean, the idea that there's a set which doesn't have an RE subset, you start to tickle you, and it still has got an air of we are exploring something. We are getting technical information about something that is clearly related to human experience, namely what we can calculate out of Turing. And then it all starts to take off. So from 44, you get 51 from the Rice theorem, which basically says if you try to get a semantic property, you won't be able to decipher. Only trivial properties. Oh, sorry. Only trivial properties. Oh, I go too far. Come on. Reminds me of my TV control. It's only got 3 buttons. It must be me, not the control. And then you've got John Myhill's beautiful analysis of creative sets, which are designed in order to understand better the structure of Gödel's theorem. Then comes the functionals, Myhill-Shepperton, Friedman-Mushnick, Kreisler, Schoenfield-Seyton, and so on. So suddenly the thing takes off. These are just some classic theorems. There are many more. Rice did lots of interesting things, for example. This is an interesting thing. I put 49 to 70. In 1949, Davis, of course, does the first work on Hilbert's 10th problem. Post had already observed that the Hilbert's 10th problem is essentially a decidability problem, and he thought this could have an undecidability result. And Davis is a student of Post. And by the way, bounded quantifiers are involved in this work of Davis in 1949. So worth having a look at. And then Julia Robinson starts to work on it, Putnam enters the picture, but and so you've basically got exponential diaphragm times by this hyphen, And then from Leningrad, Matyasevich produces new techniques of the time to finish off the Diophantine theorem, which is, of course, the statement that polynomials are enough to define RE sets. Okay? Definability. Simple multi-value polynomial is enough. So, am I going backwards again? Right. And to come to an end in this part of the theory, I think we just draw attention to Hartley-Rogers, because Hartley-Rogers devoted he wrote 1 or 2 papers, and then he just devoted himself to reading the entire literature and coding it into this magnificent book. You can get it as a Dover publication. Dover, a wonderful American publisher that republished classic works, and this has now entered the Dover catalog. But this is a massive book in which he tried to put his arms around all the literature. So in addition to theorems and chapters, it's the exercise, endless exercises for which, if you wanted to solve them, you end up having to realize that this is not an ordinary student exercise. This is basically taking some of these results from the papers of general symbolic logic and saying, go and prove those. Lots of fun, right? And there's lots of stuff in the exercises because he had a view of what the orthodox theory was, and he really liked hierarchies. He really, really liked hierarchies. He got lots of chapters. So what we've got an irony. The irony I want to draw your attention to is that the reduction of mathematics to logic, which starts this story for Frege and Russell, and all this exercise and all these worries about the foundations, for which Hilbert, of course, is extremely well known and famous. By the time these people have had their way, the reduction of logic to mathematics, and it kind of starts with school. Suddenly, mathematical logic becomes a subject in itself already by the 50s. Already by the 50s. You know, if you're staring at the Miles-Jefferson theorem, you are enjoying it for itself. You're not thinking, oh, this puts a new perspective on humanity's epistemological capacity. So mathematical logic really starts to take little interest in philosophical problems. And of course, new things come along. So, quick one. Generalizing elementary computability theory. So how do you do a generalization? Well, normally there's a phenomenon that's really intriguing, and there's some specific mathematical analysis of it. But once that's settled and it works and people are happy with it, people then take aspects of it and make different generalizations. And that's a simple pattern to say, what should you expect if you're looking at generalization of computability theory? So here's an example. The continuity, you know, the idea that something could be continuous as an object or a process, had finally a good theory. It's called the theory of functions of a real variable. Continuity, possibly sticking with a bit of differentiability. And so out of that, all sorts of things come. You get geometric spaces, you get topology, you get formal spaces, and if differentiability was involved, you'd end up with your smooth manifolds and so on. And of course, the spaces over there are defined only to define the continuous maps. That's their purpose. That's what they're there for. So in case of computability, it's a much more complicated thing to see the connection with the arrows. So there are plenty of computable objects and processes and reasoning. And of course, we have got now the classic theory. This time it's the theory of functions on the natural numbers or on strings. And what are the generalizations? Well, of course, you can do non-real numbers. You can worry about resource bounds. There is the wonderful world of higher types. And of course, there are ordinals. But there's also other things. You can take the numbered structures, which would be a modest looking generalization, because we've seen Gödel numbers and that can be expanded. And the Russian school did wonders in that area. And in particular, there are just general algebras. and of course, much more abstract things like domains, which can support some sort of computability, albeit inspired by higher types. But of course, the key question is, to generalize computability, the first thing you should think about is, let's get away from the natural number. So it's a matter of data. So the easy thing to say is, I just want to have a computability theory that is not restricted to the strings and the natural numbers. And now you get into all sorts of subjects which are self-contained essentially. And of course, we do a lot of computable analysis here. So higher types here. So we know some of this from hindsight. Anyway, here's an example of one that I was participant in as a sort of side outlier. Jens Erik got very interested in generalized recursion theories and ran projects for many years in Oslo with all kinds of activity, and you'll know these people. And the fruits of these things I listed here, various works and conferences, and then of course there's Doug Norman's work, including one with John Longley. Jens wrote an axiomatic approach to computability, which he was building on work of Kavakis, and so on. And out of this comes the theory of domains, written by Viggo Stoltenberg Hansen, which really contained a really solid mathematical account, and had lots of interesting things in it, not least Uli's work on totality. You're giving me away by your...
5 minutes for that work. But now you start talking.
It's not an accident. I wanted to be the last speaker, by the way. Anyway, are we done that one? Yeah. Okay, well, I'm going to try and be well behaved. So I'm going to say, well, a question is, what did computability theory ever do for algebra? So here are the gallery again. This is Greta Hermann, and worked with Emmy Noether. And of course, this is Bartel van der Weyden, the young Dutch fan, all in the Göttingen circles. And basically, the constructivists, after Dominic and so on, got interested. So Jules Molk, he was involved with Koenig, and he started to look at certain things in algebra from a constructive point of view. But the big news was Hilbert's solution of the basis theorem for polynomial ideals, which used non-constructive methods. Much later, Noether and Hermann were working on this problem, and Hermann produced wonderful papers that showed that the Hilbert basis theorem, or versions of it, had an algorithmic approach. In other words, the ideal membership problem for polynomial rings is decidable. Not that she was using computability, she simply gave a method to answer the question, is a polynomial in an ideal that's finitely generated or not? Now, van der Weyden wrote one of the most important books in 20th century mathematics in the 30s, and it was called Modern Algebra. And it pulled together all the algebra you and I know. And he did it because he wanted to serve something that was brewing called algebraic geometry. He never got around to the algebraic geometry. He only managed to do all the algebra. But most of the algebra you meet, and a bit more than you don't meet, is there. And that book was recommended to me as a student at Warwick. And I found it over the years more and more understandable. It just means that it takes 50 years to understand this book, or say differently, right? But one of the things I found out as a student in Bristol, because I had an old copy, was that in the first edition, dropped in the edition that I had, was a whole section on the constructive theory of fields and how you use constructive intuitionistic methods to solve problems in fields. So there was already some interest in that. But of course, oh, and now we shift gear a little bit, because the idea of applying this thing, which had already been seen in church with the number theory and solvability problem, attracted posts who managed to show that the equality problem for semigroups was undecidable. And that got Turing interested in the word problem for groups. And he thought he had it, but he did not. He actually had a stronger result than Post, a more complicated one, which he published here in the Annals of Mathematics, the well-known mathematical journal. This is an off-print of Turing's paper, which was sold at Hanson's auction house in the summer this year, as you can see, 22,000. Wasn't Turing's own. For example, Turing's paper on proof theory and where the oracle is invented, that was Turing's own, which Turing's mother sent to Norman Routledge. That went for 84,000 duplicates. The bit from the History of Computing collection at Swansea University didn't quite cut it. So we have to be content with what we can steal from the university library, if you see what I mean, without telling them. Otherwise, they'd want to be worried about insurance, and we can't be bothered with that, can we? Right, but the word problem was solved by Novikov and Bill Boone for groups, and suddenly we have important things happening. Combinatorial group theory buys into this. Okay, in fact, one related groups are already solved before the war. And here's dear old John Shepherdson. As you can see from the date, it's a fairly early photograph with that famous statue in Manchester of Turing. And I must say, we should always pay tribute to Shepherdson because he did many things. In particular, well, there you are, I've got models in the lecture. He wrote in Journal of the ACM, he published on register machines for the first time. He did computable field theory, which is why he's in this thing here. And later on, he revised the whole subject for an abstract model. And I can get it to change. Also on the gallery, of course, is Michael Rabin and Graham Hickman, the group theorist. Now we come to the powerhouse that is Novosibirsk, pictures of Malsev and Yershov. There could be a whole gallery here. You could have Goncharov and all the younger generation who did not all sorts of people. There's a lot of wonderful things come out of that school that we associate with Malsev. But the key thing here is that in '56, they wrote a fat paper on field theory. And they really looked into field extensions, polynomials, and it was a great paper that really exposed the power of thinking effectively. And they had questions about representations, when they're equivalent, when they're not equivalent, and so on. And that was an inspiration for Malsev to write a very famous large paper about universal algebras in 1961, which he called constructive algebras, but was about a whole theory of numberings. And not only did he have great theorems in there, but he really took this notion of numbering and showed that it was a topic of great interest in itself. Because it is the way we represent things, rather than the way we think of them as anthropomorphism, that we really deal with. So the numbering is the implementation. Meanwhile, in the same year, the answer to the question, what has computability ever done for algebra, had another answer, again, which is related to combinatorial group theory. Of course, the urge was always to go around finding things as undecidable. You always felt that you needed something undecidable. Until you've got an undecidability result, you haven't quite managed to somehow get into the zone on this. But what Hickman did was he noticed, in modern terms, the problem of these finitely presented groups that are now everywhere. And at this time, abstract algebra and group theory was growing as a subject internationally. Everywhere had group theory. Right? There was a lot of group theorists around. And in particular, he was able to show that the subgroups of finitely presented groups are precisely the semi-computable groups. And from that, he had all kinds of constructions, a universal finitely presented group into which all finitely presented groups could be embedded. And so suddenly there was an unequivocal positive use of answering a key question in algebra, because the finitely presented groups are very important. So Higman was very important there. And this is the world, if you like, that was beginning to shape my entering into the subject when I finished my thesis in 76, beginning it in 73, I guess. This was the one. And subsequent to this, Boone and Higman produced more and more amazing theorems. There are things to do with properties that algebraists of the time loved, like residual finiteness, simple groups. They all had a role to play in producing computability results that were positive. In fact, some of these results were known for universal algebras by the Russian Kuznetsov. And so we have quite a lot of interesting phenomenon there, and it was bubbling up. So there we are. And this is the simple notion. This is the notion that is out of Balcev. You have a set of codes, and the function on the abstract structure is computable if this diagram commutes, which is the same as saying this is an equation that is true. So it's an equational definition. Right, let me see where I am. References. Oh, that looks as if it could be the end. It could be, but I need to show you something. I'm going to jump over AI and computing.
That's enough talk.
That's another talk. Because there's another generalization. But I wanted to show you this one. So I showed you earlier that mathematics embedded in logic was somehow didn't happen because logic was sucked into mathematics through the geniuses of these people's work. But in our modern times, depending on your Instagram feeds, you might be fully aware that there's something called the San Francisco Consensus, which is more or less summarized by saying that AI is going to make everything obsolete. You don't need mathematicians anymore. High-level mathematicians, better than the ones we've normally got, will be performed by or outperformed by AI. Eric Schmidt, the ex-CEO of Google, goes on about it endlessly and talks about the San Francisco Consensus. Now, I don't think there's ever been a consensus in San Francisco ever about anything, but nevertheless, it sounds good, doesn't it? Right? So mathematicians, all these people, if you work in front of a screen, says Elon, your job can be replaced, right? So I'm thinking I better stop watching Instagram. But there's a revenge. And that is, if indeed mathematics goes to computing, then as far as I'm concerned, the only way computing and AI will ever survive the scrutiny of human beings, primary urges have wars with one another, or as if it gets reduced back to logic. I call that the revenge of the logicists. Thank you very much.